All right, welcome back. Today, we're putting on our detective hats to crack a classic clinical case. We've got the clues, we've got the suspects. Let's see if we can solve this puzzle together.
Okay, let's dive right in. The whole thing kicks off with a question. You know, the kind you'd see on a really high-stakes medical exam. But here's the thing. This isn't just about rote memorization. It's about really getting the why behind the what. So, here are our 5 suspects. Which one of these statements really nails what Staphylococcal scalded skin syndrome is all about? Go ahead, take a second, think it over, because we're about to jump headfirst into the evidence.
All right, if your clinical gut was telling you to go with option A, then congratulations, you are absolutely right. You've pinpointed the main culprit. But the real story, the fascinating part, is how these toxins actually carry out their attack.
Okay, so here's the absolute key takeaway. All that widespread, really dramatic skin damage you see, it isn't actually caused by bacteria growing on the skin. And that's a super important distinction. The problem isn't some local skin infection. No, this is a systemic attack, basically a hit job carried out by toxins that are traveling all through the bloodstream. So let's get into the mechanism, because this is where it gets really cool. Meet our villains, exfoliatins A and B. The best way to think of them, they're like these tiny, super specific molecular scissors. They're a type of enzyme, a serine protease, which basically means their only job in life is to cut up proteins. So the bacteria make them, dump them into the blood, and then they just travel all over the body hunting for one very specific protein, the one that acts like glue for our skin cells.
So how does all that lead to the crazy clinical picture we actually see in a patient? Well, let's follow the trail. We're going to trace the path of these toxins all the way from some hidden infection to that widespread skin peeling that gives the syndrome its name.
And this sequence, it's literally everything. The infection usually starts somewhere you might not even look, like in the nose, or the throat, or maybe even the umbilical stump of a newborn. From there, the bacteria just start pumping out these toxins, which, you guessed it, get a free ride in the bloodstream. Once they get to the skin, they find their target, snip those connections, and, well, the whole top layer of the epidermis just starts to peel right off.
And this right here, this explains a massive diagnostic clue. See those molecular scissors we talked about? They are incredibly picky. They only cut desmoglein 1, which is the glue holding together the top layer of skin cells, but they can't touch desmoglein 3, which is the main glue in our mucous membranes. And that's why the mouth, the eyes, and all those other mucosal surfaces are completely spared. It's a huge tell.
So you might be asking, why does this hit young kids so hard? Well, it really boils down to 2 things. First, they don't have the specific antibodies yet to fight off the toxin. But even more importantly, their kidneys are still immature. That means they just can't clear these circulating toxins out of their system fast enough. So the toxins build up and up to really dangerous levels.
Okay, so back to being a clinical detective. Your number one most critical job here is telling this syndrome apart from its really dangerous doppelganger, toxic epidermal necrolysis, or TEN for short. The clues might seem subtle, but getting this right can literally be life-saving.
Think of this table as your ultimate cheat sheet for telling SSS and TEN apart. Just look at the pattern. It's pretty clear, right? SSS, usually a little kid, mucous membranes are spared, and the skin split is super shallow. TEN, usually an adult, it brutally attacks the mucous membranes, and that split goes way deeper. You absolutely have to get this right because the treatments are worlds apart.
Okay, now that we have all this information locked in, we can go back to our original list of suspects with total confidence and just dismantle the wrong answers, one by one. This is really going to cement our understanding of the whole case.
Right. Now that we get the how and why of it all, let's just blow through these other options. First up, this idea that Nikolsky's sign is absent.
Yeah, no, that is completely wrong. Nikolsky's sign, where the skin just sloughs off with a little bit of pressure, is a classic feature of this disease. It's the direct, dramatic result of those toxins snipping away at the skin's glue.
Okay, next up, the idea that the infection is only on the skin. We already know that's not right. Think of it this way. The skin is the crime scene, sure, but the bad guys are hiding out somewhere else entirely. The throat, the nose, you name it. The skin is the victim here, not the source of the problem.
And last but not least, the one about it affecting only the mucous membranes.
Absolutely not. In fact, this is probably the single most important clue that tells you it's not TEN. The whole reason the mouth and eyes are spared is because the toxin is so precise. It only goes after desmoglein 1. So yeah, case closed on that one.
So there you have it. You've cracked the case. But the big question is,
how do you make sure all this information actually sticks in your brain, ready to go when you need it in the clinic or on an exam? Let's boil it all down.
I've got a great mnemonic for you. PLE. And how perfect is this? It's the Portuguese word for skin. So P, pulpus mucosas, it spares the mucous membranes. E, exfoliatina, it's caused by the exfoliatin toxin. L, limpa, the blister fluid is clean or sterile because the bacteria aren't actually in it. And E, escaldada, the skin looks, well, scalded. Pretty neat, huh?
And hey, to really make this stuff stick, let's connect it to the bigger picture. The only reason we can even diagnose this is thanks to the foundational work of Nobel laureate Robert Koch. You know, the guy who proved that specific germs cause specific diseases. And for a really wild parallel, think about this. The patient is basically going through a messed up version of what a crab does when it molts its shell. It's a process called ecdysis.
Okay, let's lock this in for good. Just remember these 6 key facts. 1. The cause? Toxins from S. aureus. 2. The target? Desmoglein 1. 3. Key sign? Nikolsky's positive. 4. The huge differentiator? Mucous membranes are spared. 5. Who gets it? Mostly kids under 5 because of their immature kidneys. And 6. How do we treat it? Supportive care and antibiotics, something like oxacillin, to shut down that toxin factory for good.
And there you have it. We started with just one multiple-choice question and ended up unpacking the entire story of a really serious condition, from the tiny toxins all the way to treatment. You've officially cracked the SSS case. So the only question left is, what clinical puzzle should we solve together next?